So today we will discuss on some new topics. Firstly, heat capacity. So heat and capacity. So when you hear the word capacity, it means how much, okay, how much amount of heat, okay, is involved, okay, in simple words. Now when we increase the temperature, okay, the heat transfer to a system, it will increase. So heat is denoted by Q, okay. So when we increase the heat, temperature, when we increase the temperature, okay, this heat transfer will increase, okay. So we denote it by proportionality, okay. So this will be change in temperature. So this proportionality means if we increase the temperature, this heat transfer will increase, okay. Or we can write this proportionality as Q is equal to coefficient, okay, into delta T, okay. When we add equal sign, we can add one coefficient, okay. So this coefficient, okay, will depend on the size, okay. This coefficient will depend on the size, composition, and nature of the system. This coefficient will depend on the size, okay, how large or how big the system is, okay. So usually bigger system will require higher amount of heat, okay. Even composition, okay, whether the composition solid, maybe liquid, okay, all those, and nature of the system, okay, it will depend on that, okay, this composition. Now we can write this equation as Q is equal to C delta T. So this coefficient, okay, coefficient C is called the heat capacity. So this is called the heat capacity. So this heat capacity will depend on the size, okay, the size, the composition, and the nature of the system, okay. So usually bigger size means we need to apply a higher temperature, okay. So it will depend on that, okay, size, composition, and nature of the system, and because of that this will be extensive property, okay, since it depends on the size, composition, all those, okay, and even the quantity. So when this C value, okay, is large, when this C is large, okay, it will result in low temperature, okay, or small temperature. That means when this C is large, heat capacity, okay, heat capacity is large, temperature will be small, okay. We can take it as in the example of size also, because size means we need to apply higher temperature, right? Smaller size, low temperature, okay, in simple concept. Now those system containing higher value of this heat capacity, okay, those system which have higher value of heat capacity, they will have low temperature, okay. Or we can say heat resolve, okay, heat resolve will be low, okay. This C is proportional to amount of substance. We have just discussed this now, okay. This is proportional to amount of substance. If substance amount of substance increases, this C increases. Okay, so if the amount of substance increases in a bulky way, okay, we need to apply higher temperature. Okay, so this is proportional to the amount of substance. Now let's come to a next term, okay, known as molar heat capacity, denoted by Cm. So this molar heat capacity of a substance Cm, okay, is equal to C by N, is the heat capacity for 1 mole. Okay, so it is the quantity of heat needed to raise temperature, okay, to raise the temperature of 1 mole of by 1 degree Celsius. Okay, so heat required to increase the temperature of 1 mole, okay, of a system, okay, by 1 degree or 1 Kelvin. Okay, so this is molar heat capacity. So this molar heat capacity is intensive property. Okay, so this molar heat capacity for a substance will not change. Okay, this 1 mole of molar heat capacity for a substance, it will not change, okay, with the size, okay, or amount. Okay, so this is a intensive property. Next one is specific heat capacity or specific heat. So this specific heat capacity is the quantity of heat, okay, heat required to raise the temperature of 1 unit, okay, or 1 gram mass of a substance by 1 degree Celsius. The first one is 1 mole. Okay, we talk about 1 mole. Okay, for this molar heat capacity, don't get confused with molar heat capacity and specific heat capacity. Okay, so in this case, the heat required to raise the temperature by 1 unit or 1 gram, okay, of a substance, okay, by 1 degree Celsius or 1 Kelvin. So this is capacity, it's given by Q is equal to C into M plus delta T. So this C denotes the specific heat capacity, okay, or specific heat of the substance, and this M denotes the mass of the substance. Okay, delta T, you know, change in temperature. Now all this combined together will give this one, C delta T. Okay, so this C delta T will be is equal to Q. Okay, so this will give you the heat capacity. Okay, Q is equal to C delta T. Okay, heat capacity. Okay, this will give you the heat capacity. Okay, so this one, it forms, okay, part of the heat capacity. Now remember that for specific heat capacity, this C is small letter, okay, and for heat capacity, this C is big letter. Now let's come to the next topic, the relationship between Cp and Cv for an ideal gas. So this one is important. Okay, this one is important. So relationship between Cp and Cv for an ideal gas. So if you have watched the previous video, this Cp means heat absorbed or evolved, okay, at constant pressure, okay, at heat absorbed at constant volume. Okay, this means Cv means, okay, for an ideal gas. Okay, so for an ideal gas, we are going to see the relationship between this, okay, to Cp and Cv. Now let's write the equation. Heat Q, okay, denoted by Q, heat Q at constant volume. So at constant volume, QV will be CV delta T. Okay, see, this V denotes at constant volume. Okay, so this will be is equal to delta U. Okay, enthalpy, sorry, not enthalpy, internal energy. Now same way, heat, okay, at constant pressure. So I'm writing all this in short form. QB will be CP delta T. This will be is equal to enthalpy, delta H, enthalpy. So let's take it as equation 2. Now we will find difference, okay, difference between CP and CV. Okay, so for this we will take the ideal gas equation. Okay, now for a mole of an ideal gas, okay, this delta H will be is equal to delta U plus delta PV. Okay, so this delta H is equal to delta U plus delta PV. So we are just going to, instead of PV, we are going to write RT here. Okay, the ideal gas equation is this one, PV is equal to RT. So delta U plus delta RT. Now this R is a constant, so we will bring it out. Okay, now let's take this one as equation 3. Now we are going to put these two equations, okay, the value of delta U and delta H in equation 3, okay, and find out what we will get. So we have just going to put in 1 and 2 in 3. We get CP delta T. So this delta H will be is equal to CP delta T. So here CP delta T. Now delta U is CV delta T. So CV delta T plus R delta T. Now this delta T, delta T, delta T, they are common. Okay, so we can cancel this delta T and we get CP, CV and R. Okay, so CP is equal to CV plus R. Now we are going to find the difference. Okay, so what we are going to do is we are going to minus this CP with CV, so we get R. So this means the heat capacity, okay, at constant pressure, okay, difference between the heat capacity at constant pressure and constant volume is equal to this universal gas constant. So this is the relationship between CP and CV. Next one, okay, we're going to talk about calorimetry. Okay, calorimetry. So calorie, okay, what comes in your mind is heat. Okay, metry means measurement. Okay, so in this case we are going to do the measurement of heat, okay, using an experimental, okay, using an experiment, okay, or experimental analysis. So this calorimetry, okay, means energy changes, okay, in chemical or physical process. Okay, So we use this calorimetry, okay, to determine the energy changes involved in chemical or physical processes. Now energy change, okay, in chemical or physical process, okay, is carried out, okay. So when we use this calorimetry, okay, the process involved, okay, to measure the heat is known as calorimeter, okay, calorimeter. Now from this calorimeter or calorimetry, okay, we are going to measure delta U at constant volume and delta H, okay, at constant pressure. Now you can see a diagram here. So this is a bomb calorimeter, okay, bomb. So in this calorimetry, okay, or calorimeter, we are going to determine the heat changes, okay, involved in the process. Now this calorimeter, it consists of a steel vessel, okay, this is made up of steel, okay, immersed in this water bath, okay. So this steel vessel is completely sealed, okay, and then there's a inlet, okay, for pure oxygen, okay. So here the sample is kept, okay. So in this seal tube, okay, or seal vessel, the sample is kept connected to the firing leads, okay. So these firing leads, what they will do is they will, in presence of oxygen, they will burn this sample, okay, and heat changes, okay, will take place, okay, and then the water present outside, okay, here, okay. So when heat is involved here, okay, when the sample is burned here, the heat will transfer to the water, okay, and through this thermometer, okay, we can calculate, we can check the change in the temperature, okay. So measurement of delta U at constant volume. So in this case, in this calorimeter, the volume here is constant, okay. The volume does not change, okay. Only the sample is burned in presence of oxygen, okay. So at constant volume, okay, we know that delta U is equal to Q minus P delta V, okay. So at constant volume, delta V will be is equal to 0, okay. So this formula becomes delta U is equal to QV CV delta T, okay. So this heat capacity, okay, we can calculate, okay, the heat capacity, okay, at constant volume, okay, from this experimental analysis. Now the next one is delta H, okay, measurement of delta H. That means it will be at constant pressure. So this one you come across it in your daily life, okay, from polystyrene cup, okay, while drinking coffee or tea, okay, we usually use this from polystyrene cup and drink, okay. So there is a thermometer inserted here, okay, and this is the reaction mixture, okay. So this reaction mixture, it is kept at constant pressure, okay. So the pressure here does not change, okay. Whatever changes will take place here in the reaction mixture, okay, and heat evolve, okay, will be measured by this thermometer, okay. So at constant pressure, we write Q as QP, okay. So that means at constant pressure, delta H is equal to QP, it will be equal to CP delta H, okay. From here we can find out the heat capacity, okay, at constant pressure. Now this heat evolve, okay, or absorb at constant, I'm writing in short form, pressure. So heat evolve or absorb at constant pressure, okay, is known as, is called as enthalpy of reaction. Okay, so heat evolve or absorb at constant pressure is known as enthalpy of reaction. Okay, so enthalpy we know, right? Heat. Okay, heat of reaction. So this is denoted by delta RH. Okay, delta RH. So if the reaction is exothermic, okay, QP will be negative. Okay, in the same way this delta RH will be negative. Okay, now for endothermic process, QP will be positive. In the same way this delta RH will be positive. Now with these two process, okay, with these two calorimetry process, okay, we can calculate the heat changes. Okay, so these two are not that important for exam point of view, okay, but these two will give you a clear concept, okay, why we are studying this one, okay, or how in practical way, in practical or daily life, how we can calculate these heat changes. Next one, let's solve a problem 6.6 from your textbook. 1 gram of graphite is burned in a bomb calorimeter in excess of oxygen at 298 Kelvin and 1 atmospheric pressure according to the equation C plus O2 CO2. During the reaction, temperature rises from 298 Kelvin to 299 Kelvin. If the heat capacity of the bomb calorimeter is 20.7 kJ per Kelvin, what is the enthalpy change for the above reaction at 298 Kelvin and 1 atmospheric pressure? So in this case, heat capacity is given, okay, to 20.7 kilojoule, and what we have to find is enthalpy change. Okay, that means we have to find delta H here in this. Okay, solution given M 1 gram here, 1 gram, 1 gram, 1 gram, T1 as 298, okay, Kelvin, 8 Kelvin, T2 299 Kelvin. So delta T will be T2 minus T1. So 299 minus 298, it will be just 1 Kelvin, and CV, heat capacity of the calorimeter, okay, it's given 20.7 joule per Kelvin. Now what is the enthalpy for the above reaction at 298 Kelvin and 1 atmosphere? So for this case we have to find delta H. Now we know that the heat absorbed by the calorimeter, okay, heat absorbed by the calorimeter, we can write it as Q is equal to CV delta T. So this will be at constant volume, okay, So in this bomb calorimeter, okay, we know that it is done at constant volume. Okay, so CV delta T. Now in this case the temperature rises, okay, from T2 to T1, okay, to 98 to 99. Okay, that shows that the reaction is exothermic, or let's take it as exothermic process. Okay, now delta U will be minus CV into delta T. Okay, because it is an exothermic process. Okay, so we will just add the values: minus 20.7 kilojoule per Kelvin into 1 Kelvin. Okay, so what we'll get is, we'll cancel this one. It's minus 20.7 kilojoule. So now, okay, now delta U for combustion, so combustion of 1 gram, okay, 1 gram of graphite, okay, or graphite will be this 12, okay, come from the carbon, okay, carbon 12, okay, 12 gram mole into minus 20.7 kilojoule divided by this gram. So this will give you the combustion of 1 gram of graphite. Okay, so 1 gram of graphite means 1 gram of this carbon. Okay, so what we will get is, we'll cancel first these two. Okay, so after calculation, what you will get is 2.48 into 10 to the power 2 kilojoule per mole. Now we know that, okay, I'm writing short form. We know that delta U is equal to delta H plus delta NG RT. Okay, so in this process there is no change in the number of moles. Okay, number of moles. So there was no change in the number of moles. You can see in this reaction, okay, there was no change in the number of moles. 1 plus 1, so sorry, 1 1 1. Okay, so 1 1 1 moles. Okay, no change in the number of moles. So that means this delta Ng will be is equal to 0. Okay, so therefore delta this H will be simply is equal to delta U. Okay, so 0 into RT will be 0 only. Okay, so what you are left with is delta H is equal to delta U. So we got delta U as minus 2.48 into 10 to the power 2 kilojoule mole per mole.